So thank you all so much. And like Alex said, we're transitioning into a time where we're going to talk about tools and methods. So what Paul and I are hoping to put forward in this presentation is to talk about how you can combine your human perspective and experiences during fieldwork and reference that while you're making a geologic map of a landing site, but also tying in the tool of machine learning and how we can use some more automated approaches and multidimensional image analysis to refine those maps. So um, just to kind of give a perspective view of one of the areas that we're going to be looking at. This is a northeast view along Faustini Rim from Faustini Rim A landing site. And the leftmost image is the NAC 1 meter monochrome mosaic for that area, where the bright area on the right side of the image, on the southeastern side of the image, is the slope going down into the crater. The CO2 traps are shown in the central image, where dark blue is more likely to have lower sublimation rates. And then the image on the right is slope, where yellow can be around 20-degree slopes. Next slide, please. So again, we're drawing from our own field experiences, safety considerations, science priorities. So those are our human perspectives, and then tying that to machine learning. So the way that we're going to show that we did this in this talk is to first test the technique on Earth, visit a field site on Earth to define its lithologies, use our observations to train a machine learning algorithm and compare those results with a USGS map, and then apply that to the moon. So combine those three pictures that y'all saw in the first slide, the NAC imagery, CO2 traps, and slope, combine that into an image with multiple dimensions in order to produce a machine learned map, and then compare those maps to a human produced map. Next slide, please. So this is a field site where I had a student work in the past. It's Steens Mountain and the Alvord Desert in southeastern Oregon, with a context map for kind of greater location in southeastern Oregon. On the left side of the image, or on the western side of the image, where you see all the valleys coming down, those are coming down off of the western slopes of Steens Mountain. And on the right, where you see some lighter materials, that is the Alvord Desert. Next slide. So some of the lithologies we saw were playa and sedimentary rocks that had volcanic clasts, including those that had been cross-bedded. Next slide. We saw tuffs, andesites, and rhyolites. A lot of those were forming cap rocks in some of the table mountains within the Alvord Desert, but also on the steep slopes and back slopes of Steens Mountain. So the pink rocks are the rhyolites, and we also saw some interbedded ashes within the andesites. Next slide. Basalts of various flavors. These are Steens basalts, so they're the oldest members of the Columbia River flood basalts. There's really nice thick stacks of columnar basalts, some of which are weathering out like the ones on the right. Next slide. And then finally, younger basalt flows that are more fresh and still have some pressure ridges and things like that preserved. Next slide. And lastly, we saw valley fill from some of the glacial valleys on the western side. And then there were also some nice talus slopes and colluvium exposed. Next slide. So we can make a 3-band image from Sentinel-2 data. Bands 12, 11, and 2 can be used to identify different flavors of geology based on their color when the multispectral image is produced. Next slide. And then we can bring that into ArcPro and begin a training algorithm. So we take notes from fieldwork. All of the small polygon areas in the segmented image on the left are places that my student and I either saw or we hiked to and made notes on the lithology. So you don't need the entire place to be classified, just some smaller areas where we were able to note the geology in that area. And then brought that into the training samples manager within the image classification tools and use that as our training scheme to define the units on the map. Next slide, please. So when we use the training algorithm, the supervised machine learning, letting the computer know where we had been in the field, we produce a machine learning generated map, which is the map on the bottom, and compare that to the USGS map on the top of this slide. So the two maps are relatively similar. The tuff was able to be picked up that we saw. Some of the glacial till units that we saw were preserved and were mapped within the machine learning generated map, and the plies were able to also be reproduced pretty well. Next slide, please. So we also then wanted to take that tool and see if we could apply it to one of the South Pole landing sites. So we have a map of slopes or slope imagery, ice deposits, and then a NAC 1 meter mosaic. And each of those were converted into a one band image. So we're just looking at, white to black, all shades of gray in the middle, and then combining those into like a multispectral image where slopes then become red, the ice deposits green, and the NAC imagery blue. And so the colors within that image are representing a combination of those three values. So you're getting 3 dimensions within an image without having to try and analyze the separate images. Next slide. Then that image is segmented. So we use an ISO clustering algorithm, which is kind of like a k-means algorithm, but you're not specifying necessarily the number of classes that you are requiring to be produced. And the goal of that algorithm, when it goes to cluster, it's looking for pixels that are nearby that are similar to the pixel that it starts with. We ran this multiple times to see if we got substantial differences in segmentation, but you don't see extreme differences. So for example, if you have a pixel on the slope going into Faustini crater, a pixel is defined by its slope, by its texture from the NAC images, and from the lack of ice or the high sublimation rate that's expected there. And so the computer is able to search all the pixels nearby and see if they have a similar sublimation rate, a similar illumination, similar texture, and then define those boundaries. But it starts with a segmentation algorithm like this, just dividing the picture up into looking for similar types of pixels. Next slide.
2 minutes.
So this is the final product out of that. So on the left, you have a machine learning produced map. This is unsupervised machine learning, which is different than the machine learning we used for the Earth analog site, because obviously we haven't been here, so we don't know exactly, at this site we saw tuff or at this site we saw andesite. So here we have this like multi-dimensional raster with slopes, CO2 traps, and the texture from the NAC mosaic, and it's looking for similarities within groups of pixels in that multidimensional raster. So on the left, we have steep slopes with and without ice, shallow slopes with and without ice, intermediate slopes with and without ice, and texture kind of existing in the background of that. And then on the right is the human produced map. This is the map that I produced. This is shown at 1 to 5,000, but I mapped it 1 to 1,000. And when I defined my units, I really paid attention to the difference between an intermediate slope and a shallow slope and then the steep slope, because I know that that's a safety concern that we dealt with the Artemis 3 geology calls, was thinking about that 20-degree slope. And I did not train the computer to do that. So if you're looking to compare these two maps, if you just remove those dark blue regions and make them orange in your mind, there's very few differences between these two maps. So I think that using machine learning is not necessarily like an end tool, that this is the thing that we're going to let make maps for us, but it's a really good tool for checking our work and for seeing if there are things that we might have missed during our own mapping. Thanks.